Okay, so we're going to look at the use of geometric series within our financial maths. Okay, and there's kind of two uses for this, I suppose. Really, one maybe is more um, popular, I suppose, in the exam questions than the other. But obviously, we're going to consider both, and we're going to kind of look at how we would set up the questions, which is often kind of the hardest part, really, and then going from there, kind of I suppose then how we kind of finish it out. But really, it is the setup that kind of is the trickiest part, I think, for people. So obviously we know a geometric series is a certain kind of sum of values which are increasing, where each term, I suppose, in the geometric sequence increases by a common ratio, so it's multiplied by a common amount. And obviously if we think about our financial maths in terms of increasing by a growth rate and things like that, that is obviously going to be a multiplication of a certain rate or a certain percentage, and kind of percentage increase, I suppose, in that sense. So really that's partly where we come with this idea of being a geometric sequence, and of course then a geometric series, because we're kind of adding up subsequent or kind of a certain number of terms within our sequence there. So when we're setting up our series, and I have that kind of point here, I suppose, when we're setting up the series, we have to pay attention to at which point the payments are made, and that is a very important thing to note here. And we will look at an example or two that kind of highlight that. But where the payments are made obviously has a big impact on the value, and kind of the overall sum of the payments, and it also has an impact on the interest, because if a payment is made at an end of a month, for example, then it won't accrue any interest because it won't have been sitting there for a month's time, and that can come up at maybe when the investment ends or something like that. So the other place, I suppose, we look at is we look at the monthly equivalent rate and all of these things that we've already looked at in previous sections, and kind of how we can kind of use all of those together now. So in terms of looking at it in terms of installment savings, so if we say, for example, we're saving a constant amount at the start of each month over a number of years. So let's say, for example, I am saving €500 every month for a number of years. Okay, if I start in year one, um, and sorry, every month. So let's do month one. I am putting in €500 into my bank account. Okay, and then in month two, I'm going to put in another €500. And in month three, I'm going to put in another €500. And let's say I do that for a full year. So 12 months. And I want to see what I'm going to have at the end of those 12 months. Okay, well, for each month that is sitting in my account, it is accruing interest. Okay, and if we think about this as a monthly interest rate, then that interest is going to really depend upon how long my investment has been sitting in my account for. And where this comes back to, I suppose, that we've already looked at or looked at previously, is this idea of a future value. So the future value, or the value after a certain length of time has passed of an investment or of a principal amount of money, is given by this formula. So F is equal to P times 1 plus I to the power of T. Okay, and this is a formula we've seen before and we've used. But if I look at, say, this first €500, that is now going to sit in my account for the full 12 months. Okay, at the end of every month, it is going to accrue interest for an entire 12 months. So the future value of that €500 is obviously the 500 I started with times 1 plus I to the power of 12. The same, I suppose, goes for the next €500, except it was put in a month late, so it is one less, 1 month behind the previous one. And the same thing goes with the next one, 1 plus I to the power of 10, and so on and so forth. And to find the overall amount I would have in my account, I would add up all of these future values. So I'm not just adding up the €500, because obviously that's not what will be in my account. I have to consider the fact that there would be interest in the account as well. So actually the €500 I put in at the end of the 12 months is worth more. Okay, is worth more than €500, and obviously that's going to be largely dependent on the interest rate there and the growth rate overall. But I suppose the more important thing to consider here is that we started by looking at each individual payment or each individual investment, but at the end we end up with a sum which we hopefully recognize as a geometric series with a common ratio. And with the way that I have written here, this ratio technically would be 1 over 1 plus I, because we can see that that rate is actually decreasing from each subsequent month. And we'll see how we maybe tackle that in terms of some of these questions here. So what I have really here in the text, I suppose, is just me explaining that again. So we're looking at the future value of different installments that are paid over a certain length of time. So in terms of writing this as a formula of sorts, we would use what we've done there. So setting up each of these payments and identifying how long it's going to sit in the account for, and the resulting, I suppose, in interest generally that kind of is earned upon it. And that leaves us with this formula here. I suppose this is not a formula that is really supplied for us. So I am always cautious maybe on kind of highlighting it here, I suppose. I think it's important for you to be able to set up the sequence as well, and that is something that they do request in some of these questions. I've also put a note here about avoiding rounding until the end, and that's primarily because so many of these questions here, and we see all this in our sequences and series as well, so many of these questions are going to require kind of unusual ratios or unusual decimals within the calculations there. So I think it's just important maybe to leave those decimals until the very end if we can, and it just ensures a bit of accuracy there. So we'll get into the examples here. I'm going to primarily focus on this installment in this one, and then I might do a separate one for the pensions and kind of how that's all kind of related here. So we're going to focus primarily here on kind of these future values and setting up the sequence or the series with those. So if John saves €250 a month in a savings account which offers an annual equivalent rate of 5%, how much will he have in the account after 4 years? Okay, so he's saving monthly, but the rate seems to be annual, so we're going to have to deal with that first of all. So I'm going to say that a yearly rate of 5%, which is 1.05 for 1 year, is the same as me having a certain monthly rate for 12 months. So we make sure that we match up the compounding period with the length of time and ensure that the length of times match up across there. So that's going to give me, let me see, the 12th root of 1.05 minus 1 equal to m, which means that m as a decimal is, C, the 12th, sorry, the other one, the 12th root 1.05 minus 1 is 0.004074. Okay, we'll go with that. That's plenty of decimals there. Obviously, that's around about 0.4%. Okay, so we are looking at this savings that he's making, €250 a month, and he's leaving it there for 4 years. So if we start with the first payment that he makes, that first €250, that is going to sit in his account for the full 4 years. If it's happening monthly, that is 48 months. So he is going to earn interest every single month on that first €250 for the entire 48 months. The next €250 that he puts in, it is again going to earn interest. However, it will be less interest because it hasn't been in for the entire length of time there. Okay, it's only been in for 47 months. Okay, it missed the first month, and so on and so forth until we get down as far as where we have the second last payment, which is just going to be sitting there for 2 months, and the very last payment, which was just made just at the start of this month. So we have to think about, let's say this is, we're at April now, so let's say we're looking at this situation now. If I put a payment in on April 1st today, if I put the €250 in at the end of April, okay, 30 days has September, April, yeah, so on April 30th, okay, that will have earned interest, okay, because it's been sitting there for the entire month. So even the last payment there will still accrue 1 month's interest, okay. So a trick we can do for these ones where we're focusing on future values here, one of the tricks we can do is to swap around the order of the sequence here. And the only reason I do this is to simplify my calculation a little bit. I suppose the reason being that now, having swapped it around, my common ratio is increasing, okay, rather than being a fraction, and it just makes it a bit easier then to go to that sum of the geometric series. So in terms of doing that sum, hopefully this part I suppose should be quite familiar to us. We're using our sum of a geometric series formula where a is the first term, and since I've written the sequence in this order, I need to ensure that that is what I start with. The common ratio, okay, as we know, we would generally take one term and divide it by the previous term, but we just look at the terms and see what is it increasing by, what is it being multiplied by, and it's being multiplied by the interest rate there. and the length of time, or the number of terms, then of course 48. So this is S48 of 250 times 1.004074, 1 minus 1.004074 to the power of 48, all over 1 minus 1.004074, and inputting that into my calculator gives me an overall answer of 13277.92. So putting in €250 every month for 4 years brings me up to kind of that amount there. Okay, which I suppose does kind of seem reasonable enough. Okay, you're looking at kind of, at least for 10 months, 2,500. So it seems fairly fair there. Okay, so that idea, I suppose, of just setting up the sequence really being the biggest thing that we have to consider there, in terms of those ones there. Okay, so I'm just going to skip over the next one ever so slightly, just to look at some of the exam questions here, because as I say, I want to focus mainly on the future value idea here. So we'll just kind of quickly look in at one of these exam questions here. Yeah, so start with this one. So how long should an investor continue to make monthly investments of 1,000 at a rate of 3% paid and compounded monthly if she wishes to have at least 100,000 in a savings account? Assume the first payment is made immediately and the last payment is made on the day that the investment matures. Okay, so we have a bit to kind of work with here. Okay, in this question, it is probably in our best interest to consider the last payment first, because they've mentioned that specifically here, and I think it's interesting for us to look at. So they've said the last payment is going to be made on the date the investment matures. So that, for me, means that the last payment of €1,000 will accrue no interest. Okay, because it hasn't been sitting in the account for very long at all. I've paid in €1,000 and then I'm done. Okay, it's not gaining any interest. The hope is that I'm putting that in to get €100,000. So that payment there, that last payment, has no interest. The previous payment to that will have only been in my account for 1 month. Okay, so let's say, so we'll start our question. Same kind of way we started the last one, I suppose. We're going to have to start by finding the monthly equivalent rate for an annual rate of 3%. So let's do that. And that gives me, see, we're just changing this to 0.002466. Okay, that's probably plenty of decimals there for us. So that's what we have here, 0.002466 plus, and we have 1,000 times 1.002466, and we're unsure for how long. Okay, we're unsure for how long. We don't know how many payments are required to be made here. That's the question. How long? Okay, so an interesting question for us to consider here. So let's have a look. We're setting up basically a sequence here, or a geometric series, where we know what the common ratio is of 1.002466 because of the order that I have written the sequence in here, starting with the most recent payment. That makes A be 1,000, and of course then T is this n value, okay, or n is T. It's the unknown value, it's the thing that I'm trying to work out, but I know that I want the sum to be 100,000, or at the very least 100,000. So let's try and work this out here. So 1,000 times 1 minus 1.002466, that's to the power of T, all over 1 minus 1.002466, and that should be equal to 100,000. Okay, so we have a little bit of calculation, a little bit of work to do here for ourselves. So let's do 1 minus 1.002466 to the power of T. I'm going to say that's all over minus 0.002466. And over here, 100,000 divided by 1,000 is just 100. Okay, so we're kind of getting somewhere with that one. Let's take it over to the side here to give ourselves a little bit more space. 1 minus 1.002466 to the power of t equal to, what is that going to give me overall here? Minus 0.246627. So let's do a little bit of work here on this one. We'll keep our minus here for the moment, and we can deal with it in a second. So that's going to give me minus 1.246627, 1.002466 to the power of t equals 1.246627. Okay, I'm going to convert to log format now, so I'll just do a quick little base, working for me, base power answer, and we know when it goes to log format it has to follow BAP. So 2466 answer 1.246627 equal to t. Okay, that idea of base answer power, and that is going to give me a t value of, let's work it out, 002466 1.246627. That's going to give me 89.502. Okay, we know from our work, hopefully with sequences and series, that n, that term value, always needs to be a whole number value. What this is telling me is that I need to go to 89.5 to be sure that I have 1000. So to be 100% sure, or the nearest term would be 90. So that's 90 months. So I need to invest this for 90 months to be sure that I had 100,000 with that rate, with that idea of I pay the last payment the day that the investment matures, and so on and so forth. Okay, so hopefully we're kind of getting a sense here of how important it is to just be sure when we're setting up those sequences and those series, to just make sure that we're following that idea of the future value. Okay, so that we use that in setting up the sequence, and that we kind of identify that how long each individual payment is going to sit in the account for. So let me see, we can maybe do a quick little look at one more of these. We'll do a quick little look at one more, and then we can look at the pension ones. So let me see, is there a short one here that we could do? We look at Ben here. So Ben wants to save some money so that he can have 40,000 saved for his unborn daughter on her 18th birthday. On that day that his daughter is born, he begins making equal monthly payments into an account that pays 3.5% AER, which is paid and compounded monthly. His last payment in the account is due 1 month before his daughter turns 18. Calculate the monthly payment required to achieve the fund in the time given. Okay, so let's have a little look at this one, and this one's quite topical, and we'll see kind of why, I suppose, when we move on to the next section. But just to kind of start ourselves off ever so quickly, we're starting with 1.35 for 1 year, the same as 1 plus m for 12 months, which means m is the 12th root of 1.035 minus 1, which puts m at a value of 1.035 minus 1, 0.00287. Or we'll just go to 0.00287 there maybe. Okay, so that's my monthly interest rate that I'm going to be working with here. We need to set up the situation that's happening here. So he's making payments of, we don't know. Okay, he's making a certain payment, we'll call it P, at an interest rate of 1.00287. The first payment that he makes is on the day she is born. That is going to sit in our account now for 18 years. 18 years by 12 months is 216 months. So that first payment he makes will sit in his account for 216 months. So in terms of just working out that individual one, we are looking for what is the value of this payment after 216 months at this interest rate. The next payment that he makes will sit in his account for 215 months. And so on and so forth until the very last payment, which they have told us in the question is going to sit in his account for 1 month. He makes it on the month before his daughter is born, so that last payment will sit in his account for 1 month. So what we can do then, I suppose, to hopefully make the question just a tiny bit more kind of easier to look at, is we can just rearrange the series into the opposite order, then I can start by saying that A is, of course, the first term. My common ratio is basically just the interest rate there with that 1, the kind of increasing or growth factor there. The length of time is 216 because it's in months, which matches up with my interest rate. We'll set up our SN formula. So we're looking for S216 of P times 1.00287, 1 minus 1.00287 to the power of 216 all over 1 minus 1.00287. Okay, and I suppose the overall thing here is that he wants to have 40,000 in his account at the end. So we even have an answer here as well. So kind of like the last one, however, now it's P that is the unknown. So let's do a little bit of working out here if we can. So I'm going to maybe keep some of these values because I'm always conscious of decimals. I'm working them out too soon, and my calculator will do a lot of this calculation for me. 00287 equal to 40,000. And then we can say that P is 40,000 times minus 0.00287 over 1.00287, 1 minus 1.00287 times 216. So let's just fill all of that carefully into our calculator. 40,000 minus 0.00287 over 1.00287, 1 minus 1.00287 to the power of 16. I'm just going to close that overall bracket there, and that is telling me that he would need to make monthly payments of €2,439.62 to be sure that he had 40,000 in the account at the end of those 216 months. Okay, which that seems like a huge amount. Okay, that seems like a huge payment. So I'm just kind of double checking here that I've entered everything correctly, and I haven't. There we go. I can see a mistake here straight away. I was thinking that was huge. For the amount of time that he was putting it in for, I wouldn't want it to be 2,000. There we go. That seems a bit more reasonable. 133.55. That's a lot more reasonable. Okay, so I suppose important to consider there as well, as I did there, the reason kind of, was my answer reasonable? Was that kind of a acceptable, or could we believe that that would be the answer there? And I could not. I could not. Okay, so we're going to look next at the pensions and the kind of present value alternative of that.